Hello? Perfect. 昨日は1日目のRubyKaigiでした。皆さん、たくさんお酒を飲んで、二日酔いですか？どうしてここにいるんですか？でも、皆さん、来てくれてありがとうございます。Don't worry, I'm not as good as Aaron Patterson. The rest of this is going to be in English. All right, so you're all here to try and figure out how to get Ruby apps to run better when they've got memory problems. Excellent. Before that, I'm a Ruby fellow for AppFolio. They pay for me to do all this stuff, so I like to give a quick thank you to them for letting me write the blog posts and spend a bunch of their AWS budget running big benchmarks and stuff. So thank you, AppFolio. I appreciate it a lot. I've also got a new 3-month-old baby who is very cute, and if it looks like I'm really tired, I can't imagine why that is. There's no possible reason. And 2 other kids. And have you seen the Sendai City Museum? I'm just going to say, I don't know if you're into handmade maps the way I am, but go see it. The painted-on cloth maps are beautiful. Okay, now you've got Ruby stuff you want to talk about. So I'm going to start by talking about how Ruby's memory system works, about the objects and the things, because I can give you some quick tips, and that's fine. But if you really understand what it's doing, everything will work better. So we're going to talk a little bit about what it actually does. So let's talk about big, small, and tiny objects in Ruby. I'll tell you what I mean by that. There are tiny objects. The very smallest objects in Ruby fit entirely inside their references. Ruby keeps 64-bit references to stuff, and it's often a pointer to something. But there are certain objects that fit entirely in that. Integers from about -1 billion to +1 billion, symbols, floating point numbers, and special values. That's true, false, undef, and nil. All of those fit entirely inside the 64-bit reference. And the reason you care about that is because it's tiny and they're really fast. When people tell you something like, oh, hey, you should use symbols for all your stuff because they're faster than strings, that's what they mean. Symbols fit inside the reference, and there's no extra memory allocation done from the reference, whereas strings, well, let's talk about small objects, which a short string is. So those were tiny objects. Now let's talk about small objects. Small objects fit inside a 40-byte slot. So when I said a 64-bit reference, that's 8 bytes. Tiny objects fit inside the 8-byte reference. Small objects fit inside a 40-byte slot. That's short strings, that's short arrays, that's small big decimal numbers, that's class instances with only a few. I can never remember if it's 2 or 3 instance variables, but class instances with only a few. Those fit inside a slot. Now, those of you who do a lot of memory stuff know what I mean when I talk about malloc, the built-in memory allocator. A slot is cheap to use because the memory allocator is called once for every 408 of them. So it's about 400 of them at once get allocated. It's pretty cheap. So small objects are not bad. They fit inside the 40-byte slot. Certain objects can outgrow that. Like if you have a short string or a short array and you make it bigger, it can outgrow it and become, okay, we talked about tiny, we talked about small, can become a big object. And if you're used to tracking down memory problems, when I say a big object and I say it's just allocated by itself, that's the kind of thing you're used to tracking down. Every time you make a big object, it gets an allocation call all by itself. Every time you resize it, it gets a resize call for itself. When it's garbage collected, it's freed all by itself. So when I said that a small object uses a slot, and a slot, every 400 of them get an allocation, every one of these gets an allocation. So they're a lot bigger, they're a lot more expensive. If you're trying to figure out what's using up the memory in your app and what's causing a problem, these are the best ones to track down. Okay, so that's how big objects are. That's nice. If you're having memory problems in Ruby, we definitely need to talk about garbage collection, because for memory in Ruby, garbage collection's the big thing, right? Ruby has a generational mark sweep garbage collector. It's not the very best open source garbage collector in the world, but it's very good. Generational means that newer objects get checked to be garbage collected more often than older objects. If you've got an object that's been sitting around a while, Ruby doesn't check as often to see if it needs to go away, because for most programs, the most recent stuff you produced is much more likely to be garbage. If something has sat around for a while, it's probably going to be around a while more. Mark sweep is a description of how most garbage collectors work. The mark phase is when it looks at everything it can find, it looks at all the other objects they can see, and that's how it tells what you've stopped using, what's no longer available. And then sweep is just where it goes through all those things it found out you can't use and frees them up. So, mark sweep. When I say not best in the world, I should clarify, I don't mean that it's bad. It's very good. The JVM, the Java Virtual Machine, has the best garbage collectors in the free software world. So when you compare how good is the Ruby garbage collector, that's what you compare to. Everything else is not best in the world, unless they're using that. The JRuby guys get to laugh at the rest of us here. All right, so I talked about garbage collection and the garbage collector being generational. What generational means in Ruby is that it has two kinds of garbage collection. It has major and minor garbage collection. Major garbage collection checks everything, all the old objects, all the new objects. A major garbage collection checks everything. A minor garbage collection only checks the newer objects. And so when I say the newer objects get checked more often, it's because it's this combination. Some garbage collections are major, some are minor. Specifically, a major GC happens when you ask it to. It also happens when the number of old generation objects goes up over a threshold amount, when there's more than a certain number of them. And we'll talk about these thresholds a lot later. It happens when the number of shady objects goes up over a threshold. Shady objects are ones that can be seen by things like C extensions, and so Ruby doesn't fully manage them and can't necessarily free them. But those have a threshold as well. You also get a major garbage collection when there's not enough slots free after you tried a minor garbage collection. You checked all the new objects, there's still not enough slots. Okay, now let's do a major garbage collection and see if we can free some slots up from the old generation. So those are the times when you get a major garbage collection. By the way, I say when you ask for it. Let me be clear about that. Here's how you ask for it. If you say gc.start, by default what you get is a major garbage collection. It immediately does a full marking phase through everything. It immediately does a sweep where it frees everything up. You can ask it not to do that by giving it these keyword arguments. Full mark false gives you a minor garbage collection. You can also pass a different keyword argument to get a deferred sweep. It's called a lazy sweep, where it doesn't free everything up instantly and instead it does it over time. But when I say you get a major garbage collection when you ask for one, this is how you ask for one. All right, so when your app is starting up, it starts out with a small memory space. It starts out with the default number of slots. It starts out with the default everything. And it's going to continue to get bigger. I mean, if you've got something like a Rails app or a big batch job, it will get a lot bigger. How does that work? Well, it works through cycles. It works by the grow, collect, then expand cycle. And I'll talk about what I mean by that. So grow is easy. You add objects. Your code's sitting, it's running, it makes objects. When it makes objects, it uses heap space for the big objects, it uses slots for the small objects, it uses references for everything. This is exactly what you expect. Second phase, at some point you get a garbage collection. When you need more memory than you have allocated, when you cross a certain threshold for number of bytes, Ruby will automatically start a garbage collection for you. You're used to this, you've seen it before. The expand phase is the one I haven't seen talked about as much. After you do a garbage collection, if you are close enough to out of slots, it will allocate more slots. If you go over these thresholds for how many bytes allocated in the heap, it will then increase those thresholds, but it only does that after a major garbage collection. And so in effect, what happens is as your app runs, as it gets bigger, it grows, it garbage collects. If it's close enough to the sort of ceiling, to the threshold, then it expands. And it does this over and over again. Grow, garbage collect, expand, grow, garbage collect, expand, until your app is about the size it's going to be. I don't know if folks saw Nate Berkopek's talk at RailsConf in 2017, where he talks about Rails apps in particular moving up asymptotically toward a memory threshold. They grow closer and closer to the size they will eventually become, which can take a while. It can take hours or sometimes days. But it'll get closer and closer to the size it wants to be until its active set is the right size. And when I talk about the grow, GC, expand cycle, that's what that growth looks like, is it does that over and over to get closer to that top line. And it's basically going to be slower as long as it's doing that, because when it's too small, it garbage collects over and over on the way to get to that, which is slow. So that's great. We've done a lot of conceptual stuff. We're going to talk about how to fix your apps. So let's start with the advice I should absolutely give you. Let's start with what I should be telling you here. I mean, you're here hoping I have a magic trick for you, and I have a couple of pretty good ones. But first, let's give the hard right answer. Problems when you create more garbage objects makes garbage collection slower because there's more to look through, and it makes that expansion slower, that cycle that I talked about, because when you garbage collect back down, you don't cross the threshold, you don't expand immediately. The more garbage you make, the slower all of this gets. So the very best thing to do is make less garbage. There's always the wonderful boring answer. The wonderful boring answer for the garbage collector is if you don't make garbage, then it doesn't have a very hard job. Do nothing is always very fast. More efficient algorithms are nice. If you can do that, that's great. You already knew that, but it's worth pointing out. Second best is to cache or pre-calculate if there's anything that you can avoid doing a lot of work on that doesn't make garbage, it doesn't cause these same problems. Great. A third technique is you can use a smaller number of objects that are each larger. It's not that large objects are terrible, it's that large objects have a lot of overhead. But if you're going to have large objects either way, it's often better to combine several of them. So if you have a bunch of hash tables, sometimes you can use one. If you have a bunch of arrays, sometimes you can use one. Related to that, another thing that will help you a lot with garbage collection is destructive operations. When I say destructive operations, I specifically mean an operation that reuses the same data structure. I mentioned gsub exclamation point and concat here. The first one takes a string and it modifies that string in place. The second one takes an array and it modifies that array in place. Ruby will actually modify the object in place. And so that way, instead of making a new object out of the two old ones and then throwing one of them away, it'll reuse an old one. So if you're having trouble with memory, if you're using too much memory, if your memory is slow, look at using destructive operations. Sometimes they're a lot better for CPU time as well. If you are using plus to concatenate all of your strings, there's a pretty good chance that you are doing that way more slowly than you think for both CPU and memory. Destructive operations are good where they're available, and Ruby actually has a lot of them. All right, so you've done the obvious stuff. You're still seeing memory problems. You want to debug. How do you debug memory problems? Well, one of the first things that Ruby tells you is gc.stat. gc.stat has a lot of everything about your memory configuration. It can be hard to read just because there's so much there. That thing on the left is a little bit outdated. That's from Ruby 2.3. The current one has a few extra fields. It just keeps getting bigger. But obviously there's a lot there, and sometimes it's interesting. So what's interesting? Well, for the stuff we've talked about and what you want to look at, heap available slots, heap live slots, heap free slots. So live slots are slots that are used by a Ruby object in your program right now. They're slots that are genuinely used. The other two categories are basically free. And so if you want to say, how close am I to hitting my head on the limit for slots, how many slots am I using, gc.stat will tell you that. The other things, major GC count, minor GC count, just tells you how many total GCs have happened, how many total garbage collections have happened over the entire time your program has run. So if you're asking yourself, am I garbage collecting too often? The first thing to do is count. There's also a lot of other interesting stuff in there. When I talk about those thresholds that it's hard to get past, the thresholds are in gc.stat. All sorts of things are in gc.stat. So okay, that's something Ruby can tell you. What can you tell Ruby to help out with this? Many of you, especially the kind of people that show up at this talk, have already seen blog posts about the environment variables you can set in Ruby to try and tune your memory configuration. Here are some examples of those. Ruby GC heap init slots tells it how many slots to start with. So when I talk about, you have to expand over and over to get to a certain number of slots, you can actually just tell it to start with more slots. Free slots goal ratio is telling Ruby, I want 35% of my slots to be free. So if I keep using stuff until it's only 15% free, allocate me some more slots. The malloc limit and the old malloc limit are, again, these number of bytes allocated where it decides it needs to expand past it. Those are the thresholds for size. And specifically, malloc limit is the size limit for all your objects, the size threshold for all your objects. And the old malloc limit is the threshold for your old generation objects, for stuff that has already lived through a garbage collection. And I mean, why do we set these environment variables? Well, that cycle I mentioned with the expand and the GC and contract is slow. It turns a lot. It spends a lot of time garbage collecting. It can improve your startup time. So all of those blog posts that you've seen about setting the environment variables for tuning your memory, your memory config, if they work, what they do is they help your app get up to speed faster. So if you've got a different problem, those pages aren't going to help you. If you've got a different problem, setting the environment variables aren't going to help you, but that's what they do. However, if you care about startup time, have I got a tool for you? By which I mean I figured out you could put these together, and I wrote a little thing to do it. I think it's pretty good. envmem is not a standard tool, by which I mean it's being introduced right now. You get to be the first to know about it. Tell your friends. Your process expands in phases. Startup is slow. You want a fast start. You'd like to sort of have your process start after all those expansions. You can do that with environment variables. Sure, problem solved, right? Well, what do we put in those environment variables? I mean, big numbers, but what big numbers? envmem gets them from your process's gc.stat. So you run the process for a while. Now you know about how big it wants to be. Let's just start it again like that. envmem is a gem. You install it like a gem. You don't actually need to install it for your running app. It's a thing you run separately. But the big deal is after you've run your app a while, for instance, for my big Rails benchmark, I gave it 10,000 requests to get it to about the right size and then dumped gc.stat. And by dump it, I mean write to a file, gc.stat.inspect. It's not complicated. There's also a little thing that will do this in envmem, but you don't need to add a new gem at runtime. You know, this is a one-liner. You can just cut and paste it into your app. It's as easy as adding the gem to it. But then you run envmem on that gc.stat dump, and it will cheerfully dump you out a list of environment variables for those thresholds, for the number of slots, so that your app can start at that size. You know, that's all right. The next question that I would expect, you know, you're smart folks, so the next question I expect is in all of your minds is, does it work? I know that was the first question in my mind. Now, by good fortune, I write and maintain a great big Rails benchmark. I mean, using Rails as a benchmark for Ruby, which uses discourse with a bunch of data loaded into it, 10 processes, 60 threads, big EC2 instance runs, you know, thousands of requests through it. So I thought, well, that seems like a pretty good choice to find out if this does any good. And again, by very good luck, last year at RubyKaigi, I don't know how many of you saw my talk, I discovered that there was noticeable warm-up time with this benchmark, even on CRuby. CRuby has very low warm-up time. It's not like, you know, JRuby or anything. It doesn't take a lot of time to spin up, but there was some. And Koichi, then in the audience, asked me if I had any idea what that was, and I didn't really, but I speculated maybe it was memory overhead. Maybe it was time to get the memory system up and running. So I thought, well, that sounds like a pretty good test case for envmem. So this is that graph from last year. This is the, hey, look, it has some warm-up time. The arrow is just sort of across those bars. And overall, my giant Rails benchmark runs about 5 to 7% faster after 5,000 warm-up iterations than it ran after the first, you know, just entirely cold. And that was on a total of another 6,000 iterations, I think. So, okay, that was something. With envmem, running at 10,000 iterations, dumping the environment variables, and running, you know, 10,000 requests through, it turns out that even with 10,000 warm-ups, that's just noise across the top. It's basically flat across the top. You notice that doesn't slope upward basically at all. And so that gets rid of the warm-up. Basically, the CRuby guys are right. There's no real warm-up to CRuby. It's just that it takes time for those memory thresholds to get to the right place. So if I set them to the right place from the beginning of the run, yep, it's entirely flat. So that's the answer to Koichi's question. You know, why is there warm-up? Because I didn't set the environment variables at the beginning, which most people don't. But if you've got a problem with that and you want even that warm-up to go away, have I got a tool for you? Cool. All right, so all of this is kind of complicated. I mean, I don't know about you, but when I see a presentation with this much complicated stuff in it, I start to zone out. Many of you are probably smarter than I am, but I start to zone out. Anything simple and faster? I have good news. Yes. Yes, there is something simple and faster. Specifically, your OS and your libc, if you're a C programmer, comes with a memory allocator. It comes with malloc. But that's not the only memory allocator in the world. Malloc is a library. It's written by people, same as anything else. So it turns out there are a bunch of alternative malloc implementations, and some of them are very good. And especially if you run Linux, some of them are much better than what comes in there out of the box. Specifically, I highly recommend jemalloc. If you haven't seen it before, you can Google for it. I actually wrote a fairly good blog post with a bunch of graphs on it, so feel free to look at that one. But Ruby already supports jemalloc nicely. It's used in a number of very large Ruby apps already in production. Nate Berkopec and Sam Safran. Nate Berkopec does a lot of consulting for Rails Shop. Sam Safran is one of the discourse guys. Use it heavily on almost everything and test it constantly. So jemalloc is very battle-tested in general and with Ruby. And people who actually study this in large companies have definitely checked it out. The other thing, and the other reason I say especially on Linux, the Linux allocator is not very good. If you're running on a Mac, you're going to get a smaller speed up because your allocator is better to start with. But on Linux, the allocator is not amazing. So how do you do it? I say build with jemalloc. Well, how do you do it? It's a configure option. You need to make sure jemalloc is installed on the machine you're building on and the one you're running on if it's different. And so if you're using configure directly, you can just say -- with jemalloc. If you're using RVM or RBEnv, there are a command line option and an environment variable, respectively, to pass that through. But it's a configure option. You can pass it through like any other configure option. If you do that, well, again, I have this big Rails benchmark. So, of course, that's what I test things on first. How much faster? This graph makes it look like it's amazingly faster, but the y-axis starts at 25 there, so it's not quite as big a difference as it looks. No, I found the end-to-end difference with jemalloc was 10 to 12% faster. You can, again, check my blog post if you want all of the details on specific requests and what the range is on faster, but about 10 to 12%. That is not 10 to 12% faster on memory allocations. That is 10 to 12% faster across the board for the entire benchmark. The whole thing just processes requests 10% faster. To some extent, that's that jemalloc is that good, but to some extent, it's that the glibcmalloc wastes a lot of memory, and if you free up a bunch of that memory, Rails can use it for caching. But I found over 10% end-to-end speed up. For those of you in the audience silently fuming because you like tcmalloc, and I haven't been talking about tcmalloc, it's another common good allocator. I found it gave about a 5% speed up for the Rails stuff I was doing. So it's not bad. It's definitely better than the built-in allocator, but I recommend jemalloc. Great. Well, we've gone over a lot of stuff here. Maybe we should talk about what I'm actually saying you should do and kind of give the top-level overview again. So what helps? You've got an application that isn't behaving well for memory, it's using too much, or it's garbage collecting too much, or it's taking too long. What helps with this? The first one is just less waste. With this problem, as with every performance problem, the first thing is, can you find a way to do less? Can you cache more? Can you pre-calculate more? Can you just not do more? Less waste is always the best way to do almost anything. Good environment variables help if startup time is your problem. Good environment variables won't make it run faster for the whole run, but it will let it start up faster, and sometimes significantly faster. And if you're trying to do that, the envim tool can help you with that. If you want it to run faster the entire time, then jemalloc will help with that, though it doesn't particularly help with startup time. And always stay on the latest Ruby. So one thing about the Ruby garbage collector and the fact that it's good is we keep adding to it. Right now there's a bug open from Eric Wong on what's called sleepygc that uses idle cycles to garbage collect. It's an improvement. For most people, it's better. For most people, it's a significant improvement. Aaron Patterson has been working on a compacting garbage collector that will solve a fragmentation problem that I think we're going to have time to talk about. The latest Rubies tend to get significant improvements. In, again, the same benchmark I use, I tend to find 10 to sometimes as much as 15% improvement per version. And pretty soon we're going to have JIT working properly with Rails, and that will be amazing. That will probably be a large improvement when it works well. I have high hopes for you. But yeah, So if you're having trouble with memory stuff, make sure you're on the latest Ruby if you can. Do your best to move up to whatever version you can, because there's a pretty good chance that it's done some things to help with your problem. All right. Well, I tend to talk too fast. So, since I've talked so quickly, we have a little bit of extra time. Many of my wonderful listeners are very bright people, and I expect at least some of them have been thinking, this is okay. I wonder if he's going to get to anything interesting in this talk. So let's talk about some slightly more advanced stuff. Slot fragmentation. Let me tell you what I mean by that. So a slot gets used, slot gets freed. Eventually, all the 408 slots in that page get freed, and then you can free the page. Ruby doesn't like reusing slots. If a slot gets used and then freed, the problem is if something like a C extension could ever have looked at that slot, you can't be sure there isn't a pointer to it lurking in C somewhere that could mess that up. And so Ruby doesn't want to hand out that old slot to somebody new, because if anyone else has a pointer to it, they could wind up overwriting it, and it's ugly. It's a conservative way to handle it. I mean, it's avoiding a problem that is fairly rare, but it's hard to see how else you could avoid that problem. So the way Ruby does it is it doesn't reuse slots, but that means until the whole page of slots is freed, you can't reuse that page. And so all of those freed slots on that page are stuck. They're not exactly a memory leak. I mean, at some point, the last slots could be freed, you could free the whole page, but you can't do anything with them until that page is freed. So how do you tell if that's a problem for you? You've got a long-running app. It seems to have a bunch of extra memory. It seems to have a bunch of other waste that it doesn't seem to have a memory leak. It's not getting, bigger by the same amount every minute. How do you check that? And the answer is, you know how GCStat tells you, like, everything? GCStat tells you this. Nate Berkopec is actually the guy who wrote this, and I'm indebted to him for a lot of very good writing about memory. I've spent a lot of quality time reading Ruby source code, but I've also spent time watching his presentations. What he does is he checks the number of total heap pages that have been allocated for slots, multiplies by 408, and checks how many live slots are currently there. And that's basically how many slots you have that contain actual objects out of how many slots total have been allocated that could contain actual objects. That's how many of your slots are used with a real it exists right now object. And the opposite of that, 1 minus that, is fragmentation. So if your fragmentation ratio is 1% or 3% or 5%, which are common right at the beginning, are common early on, that's not a big deal. That means you've barely allocated more slots than you need. If your fragmentation rate is creeping up to 20 or 30%, you are wasting a lot of additional slots. Now, not every slot that's counted here is actually locked down necessarily. Many of those, maybe the whole page is going to be freed really quickly. Maybe it's part of a great big chunk of objects, and you're going to free them all at once. But when the fragmentation ratio starts creeping up, you should look at the possibility that maybe you're allocating a lot of objects, 1 or 2 of which last a long time, and the rest of which all get freed. Because when you do that, there's a pretty good chance that that page winds up with just a couple of stragglers that can't be reused, and you've locked down the entire page. You've lost that 16 kilobyte page. And it's not that 16 kilobytes is a huge deal, it's that you use a lot of pages, and if you do that repeatedly, you can leak a lot of pages. So you watch your fragmentation ratio, and especially if it creeps up over time, over the time your process is running, you may be locking down a lot of pages that you just can't reuse. All right, and one last thing. One more thing that Ruby tells you, so one more thing you can use to debug, and that's GC Profiler. So this is built into Ruby. You can turn on some additional information if you want it, but the basic version is there basically for everybody. GC Profiler. So GC Profiler is a tool that you turn on in Ruby to watch your garbage collections as they happen. And it will make a little internal entry for how long did the garbage collection take. Was it major or was it minor? Was it, how long did the mark phase take versus the sweep phase take? I think even the built-in one, it'll tell you how many objects, but I know if you turn on the extra object, the extra options, it will tell you how many objects it looked through. And so if you're thinking, my program seems to hang for half a second at random times, that seems like it's probably garbage collection. Is that garbage collection? One of the things that you can do is to turn on the GC profiler and see, are you getting garbage collections that take half a second or more? You can look down that list and see if you have really big garbage collections going on. Because there's actually a lot of things that can cause a random pause in a big application. Maybe it's garbage collection. Maybe it's just something that only happens every so often. And so you can have the garbage collector check how long it's pausing and see if that seems to correspond to the problems you're seeing. And specifically, I say you have to enable it. You call gcprofiler.enable. Then you run whatever code it is you want to check, and then you, I use the simplest method, which is to call gcprofiler.report, which will dump a text-formatted big table of stuff, and you can just print it out to console or to a log file or something like that. If you want to format your own, you can also get the raw data and format it however you want. But this works fine for what I do. But you can get that whole report on how long everything took and whatever extra information you've got. And if you're really worried about it, if you see some problems but you're not sure, you can compile Ruby with some additional options to put even more information into the garbage collection profiler report and then run it and see how it's doing. Cool. Well, the stuff I do, like I say, Appfolio pays for it, and I just make it all open. So envmem is in that repository. It's also on rubygems.org, so you can just gem install envmem. It's a very simple gem. I encourage you to look through the code because it's not doing anything that's difficult. Rails Ruby Bench is what I've used to verify a lot of these things. So if you say, how does he know what he's talking about? The code for that is there. You can also Google for it. I've written a lot about it in the blog. I've written a lot about Rails Ruby Bench, but it's there. And we've still got, 7 or 8 minutes. So I would love to answer questions. If anyone has any questions, line up at the 2 microphones and please turn the microphones on. Yeah, is there anyone who would like to know anything? Anything I have covered, anything I haven't covered?
Hi. Oh, thanks for a great talk. You mentioned destructive operations as a way to save memory.
Yeah.
I felt like kind of the elephant in the room is that immutability and the danger to thread safety that if you destructively change things. So I tend to avoid doing that because I want to freeze stuff, and free stuff also saves memory. Do you have any comments on the balance between those two?
Absolutely. So you're going to find that Ruby sabotages a lot of the gains you hope to get from that. I mean that in the nicest possible way. I love Ruby. It's what I do all day. But a lot of what makes that true and makes a lot of what you're thinking of possible in languages like Clojure or Haskell or the languages that do that everywhere is that they are extremely heavily optimized for immutability. And immutability is incredibly hard for the interpreter to prove to itself in Ruby. I mean, there are a few specific things like frozen strings that we're trying to introduce in Ruby 3, and it helps a little. It helps a little. But it's very hard to get Ruby to take advantage of those immutability optimizations because it's so hard to prove, and anything in Ruby can't do that. I mean, if you ever really want to prove it to yourself and you've got some spare time, pick a dead obvious case like that where you, in some actual app that you're looking at, you say, oh, well, you should be able to prove this, this, and this, and then see how long it takes you to monkey patch something to completely screw that up. If you're ingenious, it won't take you long. Like in a couple of minutes, you can probably figure out something you could monkey patch that will mess all of that up. It's really hard to get those optimizations in Ruby because it's really hard to prove that you can't change things.
Okay, thanks. That's interesting.
That's all I had. So if nobody else has any more questions, I'm, of course, around for the conference. So if you think of something else later, grab me. I'd be more than happy to talk to anybody here.